think this is the right one. Yes.
Yes, we can see it. Yeah.
So I'm going to talk a little bit about C++, and it's a bit hard to know where to start, but going to you can hear me, right?
Loud and clear.
Good. So it's hard to describe a huge language in 40 minutes, and that's what I'm hoping to do. And then I'm going to take questions, and we can fill in the things. And basically, I'm going to talk a little bit about the aims and the foundations of the language. And then I'm going to delve into two case studies, because I don't think we can talk about programming language and code without actually showing some code. And then I will drift into design principles, how C++ is being standardized, and a little word about the future, but not too much. Um, Basically, the purpose of the exercise, as far as I'm concerned, is to build a language that allows people to build really nice applications. The value um, to the world of programming language is what people do with it. And C++ has been used and is being used for an amazing variety of things. I have some pictures here and throughout the talk that illustrate it, but if you watch something in the movies, it's used for animation. If you have used any of the major applications that take a server farm, it's there. It's in your phone, and maybe even in your watch. If your children play with Lego toys, it's used to build those. Virtual reality, automobiles, spacecrafts, um, TensorFlow to get it into AI. It's a basis of a lot of that. And it's a foundation for many of the languages that people are using. So basically, the purpose of the programming language and my work with it is to enable good applications. And C++ is the result of merging two threads of development in programming languages. I mean, in the beginning, people were writing assembly code close to the machine. From there, we got BCPL and C that allows us to manipulate hardware very efficiently. Every byte, every cycle mattered. But there's another line of thought, which is that languages should be fit for humans, and humans should be able to express their ideas in the terms they use when they discuss the problems and discuss the designs. And that comes out of Fortran, and we've got COBOL and all the other languages where people build application-specific abstractions into languages. And this made it much easier to write the programs that needed those abstractions, but it also made it very hard to combine code from different communities. So Fortran was good for numerical computations, COBOL was good at manipulating records for businesses. And if you needed to do both, like to do statistics or a large database, it got difficult. And from there, we got object-oriented programming and general purpose abstractions from Simula. And so there's Bacchus there, Christian Nygaard, David Wheeler, who's one of the first people to build code and assembler. He actually wrote the first program to run on a modern stock program computer. He was my advisor at Cambridge, Dennis Ritchie, who did C. And I needed something that both needed to manipulate hardware at the low level, process schedulers, memory managers, network interfaces, and also needed the abstractions. And so I merged the two. That's where C++ come from. And a lot of stuff has come out of that over the years. Basically, the idea is general purpose abstraction that can be used to manipulate hardware, among other things. And when I talk about a direct map to hardware, in C and C++, the primitive operations map straight to machine instructions. If you write a plus on integers, you get an integer plus operation. And memory is simply seen as a sequence of objects, the way that, or sequences of objects, the way hardware is organized for that. And if you want to make more complicated things, like arrays and classes, struct, you just concatenate objects in memory. If you have a sequence of objects of the same type, you get an array. If you have different types, you get classes and structures. And if you need an indirection, you can use a pointer, which is basically a machine address with a type associated with it at compile time. And this is very, very simple. And the simplicity of this mapping is one of the reasons that C and C++ has succeeded over such a long time. It's a simple abstraction of our hardware. It doesn't have all the complexity of the hardware, but it's a good contract between the compiler writers and the machine architects, allowing us to build good software. So when we get from the machine up to things that are more fit for humans, we need abstraction. And to be able to afford abstraction, that has to be overhead. That is, it has to be minimal overhead. So the rules for C++ was, if what you don't use, you don't pay for. And what you do use, you couldn't hand code better. So if I make a really nice abstraction, it should not just be nice, useful, appropriate for its domain. It should be affordable for critical applications. And examples here, things like points, complex numbers, dates, and tuples. These are basic data types, and we use them by the billion. So they better be compact and cheap, no memory overhead, no indirect function calls, no use of dynamic memory, heaps, whatever you call it. And we can inline the basic operations so they don't get function call overhead. And sometimes we can even calculate answers at compile time. We're getting pretty good at that. So this is the idea of zero overhead abstraction. And today C++ serves a large community worldwide, about 4.5 million developers according to surveys. And according to the numbers I've seen, we grow by about 100,000 developers per year. It's not much in percentage-wise, but it's a lot of people. And it's in most of the industries we think about. It's, as I said, it's in your phone, it's in outer space and on Mars, and in simple things like coffee machines. I am a great fan of coffee for when I'm writing code. Anyway, back to what matters. It's the applications that matter. It's the things we can build with the languages. And for that, you have to look at the whole system development thing. It's not, we don't write code in just a programming language. We write our code in a tool chain, and we write it in a community where we learn our techniques and where we get our support from our libraries. And so there's lots of things that matters. I won't get into that here, but one thing that I learned over the years is that being best at one or two things isn't enough. A language has to be good enough for everything that it's being used for in a domain. Otherwise, it falls apart. And just being the best at one detail or two is not what guarantees success. Well, nothing guarantees success, but it's not what gives success. So if we read on the web or at conferences, people are really, really keen on being the very best at one thing. I'm more concerned about how to get the whole picture done, supporting people for a large set of things more or less completely. And so I'm going into the case studies here. I'm going to look at resource management and how that is done. and I'm looking at generic programming, see how that is done. Basically, both of these have their roots in the earliest C++. So I wrote a paper in 81, one of the first papers on my work, which basically says we need to manage resources well and we need to have generic programming. I didn't get the generic programming right, that came later, but they're totally pervasive in modern C++. And so I can illustrate points where C++'s strengths are. There's an application of C++. See the engineer there at cylinder head number 5. This is one of the world's biggest marine diesel engines. Reliability is very important for the people who built the software for that. And so let's look at the resource management. A resource is something that must be acquired and then released. And we have to acquire things explicitly, but it's really bad having to give it back explicitly. We all know that when people borrow things, they don't always remember to give it back. And we know that when people try to manage resources, lots of resources in a large program, you get leaks. So we have to make sure that this doesn't happen by basically automating release of resources. And even resource retention can be a problem, because if you hold on to your resources, say your file handlers or a log, for twice as long, you basically need twice as big a computer to run the program. And there's a lot of applications for which we don't have infinite amounts of memory and processing power. And so avoid manual resource management, make sure there's no leaks, and make sure that that resources are released as soon as possible. And the way that's done in C++ is by using constructor-destructor pairs. Basically, when we grab a resource like a vector, like a bunch of integers, or a file handle, we can use it, and when we go out of scope, the resources are automatically released. This is called RAII, or resource acquisition is initialization. It's a really dumb name, but I couldn't think of anything better at the time. I was busy implementing C++. Anyway, that was done by constructors and destructors. Here is sort of a simple class. It's a vector that illustrates it. And it has a constructor, which is a function that constructs objects of the vector type, here giving an initializer list of elements, and a destructor that cleans up the mess when you're finished. And this is an example of raising the level of abstraction one level. The implementation is sort of the lowest level here. There's a pointer to some element, and an integer says how many elements there are. The vector gives us the abstraction of something that can access memory, can do range checking if necessary, can grow or shrink as necessary. It's a much higher abstraction than the basic memory. And so as we go in here, the vector of double allocates memory for those four well-known constants, stores them away, allows you to use them. Vector of string stores away the strings representing some famous language designers here. And how it does it is hidden inside the constructors and destructors. You can look at the implementation if you like, but most of the time you don't. The point is that you can use this stuff here, and at the end of the scope, everything is cleaned up. The constructor is called to construct, the destructor is called to clean up the later. And this is absolutely pervasive in the C++ standard library and many other libraries. So vectors, lists, singly linked lists, maps, hash tables, sets, strings, they all follow this model there's a handle that controls the access and gives the operations, and the values are kept over to the side, and whatever holes in there can be are dealt with by constructing with the constructor, destructing with the destructor, and this all works recursively. I could have a vector of lists, of maps and such. Or when we get into more general resources like threads, lock guards, input streams, and smart pointers, again, this works. I can have a vector of pairs of threads and streams, for instance. And at the time where we leave the scope, everything is cleaned up. This is why we can't use garbage collection, because it deals only with memory, and these kind of non-memory resources has to be handled. They are quite important in a lot of the things I do. And yeah, so we saw the first signs of generic programming before. A vector is a vector of elements of some type. So basically, when I declare a generic type, then I say I want a vector of elements, of types that are elements. I'll show you later how to define what an element is, but that's known as a concept. It's basically the requirements that the vector has on its type argument. So I can make a vector of cheese, and you saw it right there, the element of t. It's implemented in terms of t's, and it has initialized a list of t, and I don't know what t is, except that it is it meets the requirements of being an element. And so I can create vectors. I can create vectors of different types. And then immediately after we have gotten generic data types, of course, we need operations on those data types. So I want to have a sort of vectors. But I want to generalize this to say, I want to sort anything that's sortable. So assuming that a vector is sortable, I can sort all vectors, but I can sort other data structures that behave like vectors, that has the properties required for being sortable. And you can look up what sortable means in the ISO standard. It basically means that you have to have a random access sequence of elements that can be copied and compared with less than. So now, given this, I can sort a vector, or I can sort the vector with a version of sort that takes another argument. So here is what I can sort the vector of integers. Here I'm trying to sort a vector of strings using the greater than operation. For this to work, I need a second definition of sort that has the argument type there. And the generic programming, again, is the backbone of the structures and algorithms part of the standard library. It creates reusable and usable algorithms that are very flexible and fast. They're based on a sequence of elements. You have a first and a last, and then that's a sequence. And so once you build something in terms of sequences, it can work for container types, element types, operations. So it's very flexible, come up everywhere. So here's an algorithm here, find Grail in V, where V is some sort of container, and find if, basically find something in LST, probably a list, that meets the criteria that X is less than 42. That's the way that the algorithms part is constructed. And in the standard library, we have about a dozen different kind of containers, about 100 algorithms. We have the concurrency support, the random numbers, the strings. The strings are parameterized with the argument types, so with the character types, so that we can have strings of, say, Japanese characters in addition to the ASCII ones that are default, or USF 8 is also used, and the numeric typing algorithms. All of these are parameterized with types, and so they are templates, and we use generic programming to do it. I started about this trying to formalize facilities for generic programming. Earlier, I'd used macros and it didn't work very well. And I decided that for something to be useful in the context of C++, it had to be extremely general and flexible. And I didn't want a language that could only do what I could imagine, because I know for a fact that when we have a group of people, usually they can think of many more things together than an individual can. I needed the zero overhead because, well, it's C++. We have to be able to do really hard systems task, and I needed to compete with the C arrays for performance with a vector and a matrix, because otherwise people would just write the old code and have the old bugs and the old overheads. And I needed well-specified interfaces. I mean, I was the one that put function prototypes into C. We need interfaces. That's the way we organize our code. And well, in 87, 89, I couldn't do all three. And I thought, I can do the two first, and we'll have to wait with the third, the interfaces. So we got templates that gives unconstrained generosity. And since 16, we've had some support for concepts, as I mentioned before, and it's now part of C++ 20. It's shipping in Microsoft and GCC, and I think there's a version of Clang that can do this. It's not science fiction. So basically, templates was very useful and widely popular, but truly ugly and gave bad error messages. So I've been working for the last 10 years getting this problem solved. There's now in C++ really solid support for constant for evaluation of code at compile time, and good specification of interfaces. So here's the way this is done. I want to sort anything that is sortable. So I want to say we require a sortable range, and then we sort it. Fine. Now this will work. Is a vector a range? Yes. Can it copy elements of type integer? Yes. Can it compare integers with less than? Yes, it can. Everything's fine. This works. Sort the vector. Here I have a list, and it actually won't work because there's no random access into a list. And so you will get an error right here that says sortable range requires random access. This is the error message. I've seen this. So basically it solves the specification problem for templates and actually makes a lot of the code easier to deal with, less error prone. And we can also start using the fact that we now have a type system for template arguments. So here we have the sort of a sortable range. That's the one that you can get with the standard. But what if I want to sort lists? They don't have random access. So I can actually quite easily do that. I define my own class forward range, and I say I copy the sequence into the vector. This is something like list, sort it and copy it back again. And you can now start expressing algorithms in terms of containers instead of what we've been used to for the last 20 years or so, expressing them in terms of sequences with a beginning and an end. So now we get here, sort the vector. It sees, does the vector have all the properties required by a sortable range? It does, so we call that. List, can you sort it as a sortable range? Nope, we're lacking we're lacking random access. Can we do it as a forward range? Yes, we can. So it chooses this. Basically, the algorithm says the more strict requirement is always picked. And so it will take the vector because a sortable range is harder to meet than just a forward range. And we compute these things straight from the definitions of the requirements so that people don't have to build rigid hierarchies of classes and such. It's all done automatically. And defining concepts is not actually that complicated. Basically, what we get is first order predicate logic. So we have a lot of background and history for how to do this. We just need a notation. And so here I'm defining the concept sortable range. I say it must be a random access range, and the iterators should be able to be used for sorting. These two things are in the standard library, so I don't have to invent them. I don't have to define them myself. This is good because the lowest level concepts are always the hardest to define because they have to take care of all kinds of messy little language issues. But when you want to define your own, or you can look up and find it in the standard for the standard ones, you can simply say that a concept requires that elements of the type can be used in certain ways. These are called use patterns. So to be a range, a type T must have an iterator member type. There must be a begin operator that yields an iterator. There must be an end operation that yields an iterator, and the and the iterator must be an input iterator. Again, input iterator is defined in the standard library, so we don't have to define that. But basically, the fundamental idea is you have a sequence with a beginning and the end, and the begin and the end operation gives you the iterator that the algorithms can use to manipulate the sequence, and that iterator must be an input iterator. I mean, this is just a slight notation for how we would describe it in English, and it's a description of how the standard have been saying it in words for a long time. The problem is, of course, that compilers don't read manuals, and so we have to have a way of getting it to the compiler, which is this. I've been helping to evolve C++ for a long, long time. It was clear from basically day one that we couldn't deliver everything needed in the beginning. And anyway, we couldn't actually know what we wanted. We needed a feedback loop. So the idea is that you build something that is useful, then you see how it's used, you see what problems there are, and you solve them. That kind of iterative feedback loop only works if you have some principles for how you actually make decisions. And so we needed to articulate principles. A language is much more than a collection of features. It's a dense web of interrelated features and guarantees and type system rules and such. And so the principles, one of them was I didn't want to solve particular problems. I want to provide abstraction mechanisms. And it's really hard to avoid people pushing. I mean, people always push for cool features, for fashionable features. And sometimes they don't actually last very well. So there has to be a choice. And there must be some trade-off between stability and evolution. People want new features. Basically, the world changes, we change, so we want to be able to evolve with that. On the other hand, when there's billions of lines of code out there, we mustn't break it. And so you have to learn. People tend to ask for three things to do with C++. First of all, they all agree that C++ is too big and complicated. I agree with that too. So we want a simpler language, smaller language. And people always ask for another couple of features while making it simpler and smaller. And whatever we do, we mustn't break the billions of lines of code out there. This is quite a quandary, and working in that space, there are ways of handling it, and it's difficult. I'll get a little bit further into it next. But basically, here are some of the general rules for C++ as I articulated them in a book called Design and Evolution of C++ in 1994. Basically, the rules here grew up mostly in the early 80s, where I was starting out with C++. Basically, it's driven by real problems. We're not going to need perfection. Theory is a great guide for how to do things, but it's not a great guide for what to do. And C++ has to be useful at all times. We can't just wait for 5 years for doing something. And we have to get from here to there. If we have existing code, it must be able to be transitioned into more modern code in some way. There's a whole set of principles that you can find in the design evolution of C++. And then in addition to the general rules, you have more language technical rules. For instance, no implicit violations of the static type system, which is something I couldn't do, but I could try. And eventually now we are getting to the point where this can be done. I didn't like the preprocessor because it's the source of complexity and bugs. The zero overhead principle was there in the early days. Basically, I realized fairly early on that you couldn't just design a language feature for feature. You had to have an underlying philosophy and you had to articulate it. So I did, and that helped. Today, C++ is controlled by a very large and active standards committee working on the ISO rules. And the question is that good or bad? Probably both. Standardize C++ under ISO rules. And of course, being a researcher, building things, no, I'm not ready. We have to finish this stuff first. We can't standardize too early, And they kept pointing out to me that I didn't really have much of a choice because their companies, which were sort of the biggest producers of computers in the world at the time, couldn't depend on code that was controlled by a corporation that may become a competitor, namely AT&T that owned Bell Labs. And they very kindly told me, of course, we could trust you, but you might get run over by a bus. So we got to standardized. There was many kinds of standardization. The hardest and the gold standard is the ISO standardization, and that's what IBM and the friends had decided we were going to do. And we get long-term stability. Long-term stability is a feature. People cannot build systems that has to last for decades in a language that's changing every year, every 3 years. So when we evolve C++, we do it on under very strict compatibility rules. Standard is good because it's vendor neutral, and it can lead to it's important for major users because they don't want to held captive by other organizations. And then, of course, there's all the dangers, designed by committee, stagnation. People have different ideas about which direction the design could be, and people tend to over-elaborate their designs. So basically, well, we got this way. And this is a picture of both the strength and the weakness of the approach. The committee started rather small and manageable, and it grew and it grew and it grew. And now we have meetings with 250 people turning up, and getting 250 people to agree to anything is really, really hard. So far, we have succeeded. C++ 20 is currently out for national vote, and everybody is going to vote in favor. So we'll have a C++ 20 standard in 2020. The first standard was in 98. We got a major improvement in 11, and I hope all of you that write C++ at least have C++ 11 available, because it's so much better than 98. 14 was a relatively minor improvement. We decided we couldn't live with the standard ISO 10-year cycle, so we changed it to a 3-year cycle. And so the idea here, we have a major release, major change. After that, we need a little bit of time. We need to learn how everything works in combination. We have to get things in that we knew we wanted but couldn't get in because of the feature freeze. We have to have a feature freeze to ship something major. So 14 was one of these, was a set of features for completing C++ 11. 17 should have been a major release, but it was sort of small to medium because we didn't get ready in time, and we work on the train model. If it's not ready, we don't ship it. We ship the standard, but we keep the feature back for the next release. C++ will be 20 will be great. We're going to get concepts, we're going to get modules, coroutines, ranges, and it's already been in places. So you can play with it, and some people are using parts of it in production. Concept modules, coroutines, and ranges. That's the standard library thing that gives you the container algorithms, are all in production in various places. I could have mentioned better concurrency here also as one of the major things. And there's several major implementations of this in use, and they're all getting close to shipping all of 20. Of course, this is not perfect. There will be a 23 and so on. We are facing a lot of challenges. New hardware developments are hard to keep up with, but we're getting better at GPUs, FPGAs, things like that. There'll be a concurrency model coming in 23, almost certainly, that will generalize our specification of concurrency so that we can do both push and pull between threads and have coroutines work and work better with threads and things like that. We are working hard on simplifying use by generalization. You saw these algorithms I was doing on containers, much easier than to write begin and end. With iterators, range for loops are easier than the C for loops and such. We try to simplify the common cases. This is the key to how you can have simpler code in a language that is bigger. That is, we cannot shrink the language, we cannot throw away features because people depend on them. However, we can provide better generalization and simplify the common cases so that the code actually gets simpler. We maintain stability, and now we have to educate the community. That's quite hard at times. It's not just business as usual. If you want to use the novel features of C++ 20, you actually have to do a little bit of reorganization to get the major benefits. Like modules can get your code to compile about 10 times faster. I have seen between no improvement and 50 times faster compilation, but you have to actually start using the modules. And we improve the language and libraries so that you don't have to write the complicated stuff yourself. And one of the things I've been working on is something called the C++ Core Guidelines. This is open source project by people in various organizations, Microsoft, Facebook, Red Hat, Morgan Stanley. And basically, we can write, type, and resource safe C++. No leaks, no memory corruption, no garbage collector, that would be overhead, no limitations on what you can express, no slowdown, and still in ISO C++. The tool support is approving because we want to guarantee this. Now you can write it, but we want guarantees that what you wrote follows the rules so that you get the major safety benefits here. And this is work in progress. You can find the core guidelines on GitHub and you can start using them. There's a tiny support library that we are trying to get out of business by getting it into the standard. That's already happening. And there's some standard and static analysis support tools. The current best one is shipping in as part of Visual Studio. One of my rules for collaborating with people is that the results has to be generally accessible, and that means that even though it was Microsoft that built it, it's shipped for free. That's nice. And you can see those guarantees here, sort of one of the holy grails of programming. So we're getting there. And so my conjecture at this stage with the experience I've got is that the most direct expression of an idea is the simplest to write. It's statically type safe because if you mess with the type system, you'll probably complicate things. It'll also generate the fastest code. It'll be the most flexible for composition and the easiest to maintain. We're trying to get there. We're not there all the way, but it's getting pretty good. And one of my slogans is to keep simple things simple. And of course, don't make anything impossible or unreasonably expensive or unreasonably complicated, but focus on making simple things simple. And we still have to remember that the principles and idea I'm outlining here is for the domain where C++ was meant for, namely applications and systems that need to manipulate hardware fairly well, and it's complicated enough that you need to handle the complexity. So that slide up front, you have to direct map to hardware, zero overhead abstraction. Where that is relevant, this is where C++ is strong. No language is the best for everybody and everything. And so I've sort of defined the domain for which C++ is most relevant. And oops, then this is sort of the end of my prepared words, and I can now take questions.
Thank you, Bjarne. Thank you. That was a very clear and straightforward introduction to a topic that we all know and agree that can be very complex.
Just a second. Let me just. Yeah. Try saying something.
Hello? Can you hear me?
Hmm.
Hello?
I'm having some sound problems.
Okay.
Try saying something now.
Hello, hello.
That's better. Okay. I had trouble
Great.
hearing you.
No problem. Well, so we have a couple of questions already gathered, but I'll just ask the host to open the chat as well so that we can get more questions.
Okay.
But we can start with the first one that is coming from Eleandro Duzentos. He's asking what strategy is used to maintain such an important project like C++. And there's a follow-up question that says, are all code contributions to C++ unit tested? If you can answer that, Bjarne, please.
One of the things that you should realize about C++ is that it's really quite an old language. And it grew up before there was any idea of a unified way of maintaining things, a unified thing um, for, for, for testing and things like that. So roughly everything exists for C++, but there's many of them. So there's many test frameworks, there's many build systems, and you have to choose, and that's trouble. It would be much, much easier if we had a standard way of installing libraries, a standard way of doing unit testing. But with millions of users and no central point, no owner that can finance the development of such things, we just don't have it. And so you have to go and you have to find something. I mean, I can think about 5 different unit test systems and 3 or 4 really superb build systems, but you have to go to the web and search them out and get some advice. Sorry about that, but you know, it was spread all over the world before anybody could try and organize something unified.
Of course. Yeah, there's another question here from Romario. He's asking, and I believe you already answered partially. What can we expect from C++ in the near future? How do you see it like growing from a community adoption?
Yeah, we're going to see C++ 20. We're seeing it already. And in there, the major features are modules, gives you better code hygiene. We will eventually get completely rid of include files and most of the macros. Finally, this was on the list of things I wanted in Design and Evolution of C++ back in 94 and before that. And it's shipping. And in 23, we'll probably get a standardized set of modules defining the standard library. Now the language features are available. So we should get cleaner code, faster compilations from that with the concepts and compile time evaluation facilities. We should get much better generic code, much better checked generic code, more flexible generic code. I expect in some years in the future, most of what we do today with overloading and simple types and type and class hierarchies will be done with concepts that are more flexible and more efficient. There's no overhead on using concepts. So if you give genericity through concepts, you will run much faster than if you give the same kind of flexibility with a class hierarchy. And anyway, the concepts are more flexible and they don't have the cost of a virtual function call, which may be cheap, but they're hard to inline. We get coroutines. Coroutines was sort of the bread and butter of early C++. The place where C++ was used most in the early days were things that required a lot of concurrency, but couldn't afford threads. So we used coroutines instead. And we lost it when Sun and others produced computers for which it was hard to implement coroutines, and now they're back. A coroutine allows you to keep state in between, implicitly keep state in between calls. So you can generate, say, a function that gives you a sequence of values where when you call it many times, each time you get a new element. So a Fibonacci coroutine, you call it and you get 1, you call it, you get 1 again, you call it again, you get 2, call it again, you get 3, call it again, get 5. You get the Fibonacci series. And so this is quite important in a lot of applications that has lots of concurrent activities. And I know it's being used in places to run 200,000 or more concurrent activities. And 200,000 threads would kill most systems. With coroutines, it's quite manageable. We're getting some better library support. We're getting time and dates that's better than is available in most places. Anyway, so there's a list, and I will probably forget something, but you can look it up in the on the web somewhere. There are lists of features.
Great.
For the future, we're working on better library support for modules, better concurrency model, better support for coroutines, and then a few other things. But we're being slowed down by the coronavirus.
Of course, yeah. Great, thank you. So there's a question from Andre. I'll actually tweak this question a little bit and make it more personal. What is the best compiler for C++ on your own programming, on your own coding, Bjarne?
I use, when I'm on Microsoft, I use Microsoft's compiler. When I'm on Linux, I use GCC. And they are both very good. I cannot say which one is the better. And Clang is also good if I was on, but dealing with three compilers is a bit difficult. The machine I'm running on here, my laptop, actually has all three compilers, so I can shift between them when I want to. But for the kind of work I do, the compilers are all good. They're all good enough. They're all better than I imagine. I see some of the code generated. I couldn't do that by hand. And so it comes down to what is your tool set? What is your environment around the compiler? What is important to you? Are you a heavy debug user? Do you need static analysis? Do you need integration with some system I've never heard of? Those are the things that determine which compiler you use, not the quality of the compiler, because they're all good.
Yeah. And what are your thoughts?
I could, by the way, I could not have given this answer 10 years ago.
Okay, so that's great for Andre. So we are getting even new feedback from Bjarne. So there's a question that from Tyson that says, "What are your thoughts?"
And by the way, all three compilers are free.
Yeah, they're all free. Andre, there is your answer. So what are your thoughts on the implementation of C++ for embedded systems? Will it replace all C-based code used currently?
I think it will replace the C eventually, but it'll take time because the implementations of C++ on some of the embedded systems are not really up to snuff. And I think most of them are now getting up to C++ 14. And if they're there, you can do it. But quite often they are sort of falling a bit behind. Furthermore, their C implementations has a lot of extensions that are vendor specific. And the vendors actually like that, because then you can't go to other vendors. It's called login. And if you are a user and you are logged in, if your C++ compiler doesn't provide the extensions that they put into their private C compiler, then you can't move to the C++ compiler. So it's going to be slow. Also, there's a lot of myth about what is fast and what isn't. For serious comparisons of performance, C++ outperforms C because the C++ compilers and the C++ language is just far better at specifying work to be done at compile time.
Yeah. Thank you, Bjarne. There is a very interesting question coming from Richard Sutter. He is asking, how do you think that the rise of some languages that can work on the same domains of C++, like Rust and Go, although having different design principles, can help improve C++?
I'm not sure to which extent Go is in the same domain. And I'm not, I think C++ is actually influencing Go and Rust more than the other way around. It's very hard to take a feature from one language and just graft it into another, because each language has its own type system, its own implementation strategies, and its own conventions for use. And so it's hard to take something and just put it into the other thing. I think more often what you see is that features and ideas sort of bubble up through research, up through practice, and then find its way into different languages. To take an example, C++ has a feature called auto that says pick your type based on the initializer. So auto x equals 7 makes x an integer. Auto y equals the string foobar makes y a string. And lots of languages have that. And people says, you borrowed it from this language here. People mentioning their favorite language. And I'm saying, no, I didn't actually. I implemented this back in '83, and it wasn't new then. There was languages that had it back in the '70s. I was just forced to take it out again because the dominant people were thinking in terms of C and couldn't quite see the benefit for it. And once we got to generic programming, it became very, very popular. But people think it was gotten from another language. It was gotten from the ideas that are drifting around in the systems world, in the language design world, in the theory world. If you want to know where these things come from, I wrote a paper for the History of Programming Languages conference, which you can find on the web or on my homepage. And it's not a short read, but you can find all that kind of answers there, including the list of things that I think I borrowed from other languages directly or indirectly, and some features I think other languages borrowed from C++.
Yeah. Thank you. Yeah. So there's a question from Luana. She's asking, what are the kind of problems that most commonly lead to a revision or update of the C++ standard?
I don't know. I mean, there's bug fixes, but that's uninteresting, and that never goes to the level where people should notice. And then there are new features which are inspired by people's problems. The most common source of ideas is roughly somebody is writing a library or building a system, and they find that they have to build libraries or use workarounds and say, why don't the language do that? Or why don't the standard library have this? So a lot of it is driven by people's needs. But you saw my list of domains where people use C++. So it comes from all over the place, and there's not a single source or a single inspiration. But mostly it comes from problems. It's always a good idea to focus on problems rather than answers or theories.
Yeah, and that's a great segue to the next question. So there's Jose Pio asking, I'll actually just tweak the question a little bit again. He says, what are the pros and cons of using C++ I would like you to focus more on the cons, since I believe the only con that was clear so far is that C++ is not for easy problems, right? It's mostly, it's better for real problems, like hard problems.
Yeah, I mean, the main problem is the complexity,
Okay.
which comes from age and from the increased range of application areas. Nobody uses the whole language. There's no individual do that. But when you have a system with many, many parts, different people emphasize different things. If you're writing the low level part of a thing doing, say, signal processing or, or network, low level networking, you are actually writing in a language that looks different from when people write a business application or the code that does the voice generation for something like what we're doing here, talking. And so the totality of the language is overwhelming. And people have to learn to not try and understand everything, but try and understand what they need from the language, and then understand that bit well. And this is one of the things that the core guidelines is trying to deal with, because the other source of complexity is the fact that there's old code. And so there's old and complicated ways of using the language that people have become used to. And then they keep writing complicated old code, quite often unsafe too, where there are alternatives, but they haven't bothered to learn the alternatives. And when you get a code base, you need to upgrade that code base to a modern style before you can benefit. The core guidelines is going to help there, and I think we will never really solve this problem until we get code transformation. Imagine a tool that looks through your code and then look for loops and see which ones can be turned into range 4 instead of C-style loops, and then transform them. Now, once you have range loops, you can look at the algorithms and see whether you have an algorithm that does this for you. You can also look at the concurrency algorithm to see if you can parallelize the operation. And that way, we could automatically upgrade a lot of loops to some parallel computations. And now, this is science fiction in the sense that it has been done in research, but not in any system I know is deployed. But I think we have to go to code analysis and transformation to get rid of the complexity that just comes from the fact that there's a lot of old code. And notice that any language that's successful over a few decades have this problem.
Great. Great answer. So there's a question from Eduardo. He's asking, can we say that with the presentation now, can we say that C++ is the most complete language today? Or in other words, does it have more generic resources than the others? I don't know if that's clear. Yeah.
I think it's clear what the question is, but no language is perfect for everything. C++ is a very broad spectrum language. It probably has a greater range than other languages when you take into account that you have to deliberately deal with hardware and that you have to put in efficiency. You can have languages that are very, very expressive, but they eat up 90% of your computer, giving you that flexibility. If concerns about performance and reliability and such comes in, C++ has a major stretch, so it's pretty good at that.
Yeah, we have more 5 minutes, and I still have a couple of questions here. There's a challenge actually for you, Bjarne. Bruno is asking, how would you integrate C++, like the libraries in C++ with Node.js based frameworks?
I don't really know. I mean, isn't that framework actually? I mean, the implementation of JavaScript is C++. So I'm
Yeah,
not. No, I don't know the details, not the
yeah,
technical details. Look it up.
yeah,
I think the people that are building Node.js actually are using C++,
yeah.
so
They
they'll
do.
have an answer.
They do.
It
Yeah,
is a C++
they do.
program.
Yeah,
You saw my early picture. I put a couple of languages up because I absolutely refuse to get into language wars.
exactly.
Most of the best languages that C++ is nominally competing with are C++ applications.
Yeah, yeah.
So I'm not going to be rude about such
Of
languages,
course, and
but
that's
I don't
actually
know the
the yeah.
details.
Yeah, no, no, you're right, and that's actually the topic of your presentation. C++, the invisible foundation of what
Yeah,
we can say hold the or the majority of the computing world
yeah, that's the
is
point. You
is
don't
running
see
on.
it.
Yeah,
Just like you don't see the internals of your engine on your car. You
of
don't
course.
want to see them actually. As long as the engine of the car was done right, you don't have to worry too much about it. Just like the libraries that you're using, say from Python, they'll be C++ mostly. It's TensorFlow and things like that. You don't have to know about them. You don't have to see them, but you really benefit from the things I was talking about today, even
Yeah,
if you've never seen a line of C++ code.
no, that's great, and that basically answered the other questions that I'm seeing in the chat. But there is one here referring to AI machine learning. So maybe you can just share your thoughts on how this is being developed so far. What do you think is realistic for the future, and what some of the C++ work on AI
I, I,
I've seen? Yeah.
I really don't know very much about that. I
Hmm.
know there's some efforts for standardizing the way C++ is used in the automobile industry and such, where all of that self-driving car stuff and the LiDAR stuff and such, image recognition, that's all C++. But it's at a fairly low level, and they are trying to standardize how it's used. And I'm not really up on that. But there's a lot of work going on in that area.
Yeah. Great.
And by the way, they need to integrate the AI with some of the concurrency work, because a lot of these systems that use AI are heavily concurrent. And
Yeah.
by the way, that again comes into reliability. If you're building rockets and planes and cars using this kind of stuff, safety is a major, major issue. And there's a lot of initiatives going on in that space. I can't think of them off the top of my head. If you need some references, send me an email.
Okay, great. So I think the last question would be, since the majority of the audience that we have here are like young Africans, like people in the ages between 20 and 30, like they're really starting in this world. Someone here is asking, it's for Fabricio is asking, what would be your advice, right, to give to these young programmers, people that are really starting in Africa,
Yeah,
especially?
it's always hard to give advice, because to give really good advice, you have to know the problems and
Yeah,
the
context.
background of the person you give advice. So I'll be fairly conventional. Um, get as much education and as good education as you can get. Um, uh, Focus on problems, find good problems to work on. Work together with nice people.
Hmm.
It's not good to work with a group of people you can't trust.
Yeah. Bjarne, thank you so much for your time, for your presentations, for your answers. It's really a pleasure having you here, and I hope you enjoy the rest of the day. We will continue with this summit,
Yeah.
Now we are looking forward to.
I will disappear, but thank you for inviting me, and good luck with everything.
Thank you, Bjorn. Thank you so much.
Bye.
Bye.